All right, in this video we're going to talk about Unit 4, Objective 3, relative extrema. So relative extrema are sometimes called local extrema, and they describe points that are higher or lower than all other points on an interval. So we've seen these things before. The points that are higher, we call those maximums, and the points that are lower, we're going to call those minimums. So you've seen relative max and mins before. They're not necessarily the highest overall, but they're the highest in a little area around it, so in its own little interval. All relative extrema will happen at things called critical points, but not all critical points are going to be relative extrema. If a critical point doesn't yield a relative extrema, we're going to call that a saddle point as well. So a critical point is either going to be a relative extrema or it's going to be a saddle point. So all of these things are going to be based on critical points, so we need to know where critical points are, and that's when f prime of x equals 0 or f prime of x does not exist. So if our derivative is 0 or undefined, we can have a maximum, a minimum, or a saddle point. All three of those things are critical points. If we think about this first example, there's a little bit more we got to talk about first. AP justifications, and then we'll look at this example here, and we'll talk about critical points and all of that stuff as well. So a function, these are going to be our AP justifications. These are what we have to put into our heads, what we have to put on our AP exam if we're going to get credit. A function has a relative maximum at x equals c if f prime of x changes from positive to negative. And if you think about that, f prime is the slope. So the slope has to change from a positive slope to a negative slope. That's going to give me a maximum. So it's not a stretch to think about the minimum. That's going to be if our derivative changes from negative to positive. And again, if you think about that in terms of slope, if the slope was negative and then the slope was positive, that's going to give you a minimum value. So find and label all types of local extrema for f of x equals x cubed minus 12x minus 5. So if we're going to tie our relative max and min to critical points and where our slope or derivative of the function changes from positive to negative or negative to positive, we're really saying if f prime changes from positive to negative, we're thinking about f going from increasing to decreasing. So we want to think about that the same way. We want to take the derivative and make our little number line. So f prime of x is going to be 3x squared minus 12. So if you want to factor that, we can say 3 times x squared minus 4, which would be 3 times x plus 2, x minus 2. So if we think about what we did before, we tried to find intervals of increasing and decreasing. So when we did that, we wanted to find when we weren't increasing or decreasing. So we set this equal to 0 to find, oops, that's a minus 2. We set this equal to 0 to find where we weren't increasing or decreasing, so when our derivative was 0. So we know f prime is going to be 0 at x equals negative 2 and x equals 2. These are going to be critical points. That is where my derivative is 0. Now we can look, our derivative is never going to be undefined here, so we have no critical points from an undefined derivative. So we take the same idea, the same approach that we did last time, make our little number line, label it f prime of x. We're going to put negative 2 and 2 on our function, or on our number line, and then we're just going to pick numbers. So take negative 3. Negative 3 is going to make this term negative. It's going to make this term negative. Negative times a negative is a positive. We have 0 here and here. Take 0, plug it in. That's a positive term. That's a negative term, so we're going to end up negative there. and then something bigger than 2, let's say 3, it's going to make this positive, it's going to make that positive. Now here's where we have to be careful. It says find the local extrema, not where are the local extrema. So we know the local extrema are at -2 and 2, but they want the y values, right? So find the local extrema. So how high does my graph go? How low does my graph go? So we know we're going to have a relative max at x equals -2, and that's going to be because f prime went from positive to negative, but it wants us to know, or it wants us to find what the actual extreme value is. So what is the value means what is the y value, not where is the extreme. So the where would be -2. So we have to find f of -2, not f prime, because we know f prime of -2 is 0. We want to know how high does the graph actually get. What's the actual y value of my graph? So we take -2, plug it into f, and we get 11. So there's a relative maximum at -2, 11. That is the value is 11. We also have a relative minimum at x equals 2, and that's going to be because f prime went from negative to positive. So to find out what that actual value is, we want to find f of 2, and that's going to be -21. So if we were to do a rough sketch, we know we have a positive slope, a negative slope, a positive slope. We know that this point here would be -2, 11, and this point here is going to be to -21. So we can see what critical points turning into max and mins look like. Just a rough look at what a saddle point would look like. If you went from an increasing or a positive slope to a positive slope, but inside there you had a slope of 0, that right there would be a saddle point. So you're going from increasing positive first derivative to increasing positive first derivative. But it's not a maximum or minimum. And your slope here is 0, right? You flatten out, you get a slope of 0 right there. So this would be a saddle point right here. So there's one more thing that we can do with these max and mins, and that's going to be our second derivative test. So there's another way that we can justify our max and mins. So a function can also, we can say, has a relative maximum at x equals c if f prime of c equals 0 and f double prime of c, now we're talking about maximums, is going to be less than 0. So the derivative equals 0 and the second derivative is negative. So what that would look like, remember, second derivative is the concavity. So we're looking at concave down. Concave down looks like that. The point where the derivative is 0 is going to be right there. So this is our second derivative test. So likewise, if f prime of c equals 0 and f double prime of c is greater than 0, we're going to be concave up, and when we're concave up and our slope is 0, we're going to have a minimum. So that's our second derivative test. We're not going to use that too frequently, but every so often AP can write a question that's going to make us use the second derivative test. A lot of times they won't tell us what the function is, they'll just tell us about the derivative. So let's use the second derivative test on this function that we just looked at. So we know that f prime was equal to 3 times x plus 2, x minus 2 after we factored, but it was also equal to 3x squared minus 12. If we take our second derivative, that's this function here, or take the derivative of this one, it'll be a little bit easier. We're going to get 6x, and that's just it, 6x. We know we had f prime of x was 0 at x equals 2 and negative 2. So if we find f double prime of 2, that's going to give us 6 times 2 is 12. F double prime of negative 2 is going to give us negative 12. So if our derivative is 0 and our second derivative was positive, we're going to have a min at x equals 2. And if the derivative is 0 and our second derivative is negative, we're going to have a max at x equals negative 2. Now notice that we can stop here at the x values by looking at the question. It says where that has any function or any max and mins, not what are the max and mins. So where is x value, so we can stop here at x equals 2 and x equals negative 2. So we're going to call it quits on that video. We'll see you in the next one.